Hello. In this video, we're going to look at Newton's law of cooling for a particular body. Now, in the question, it tells us that a body cools down from 200 degrees C to 100 degrees C in 40 minutes. And in part one, we're asked to show that the temperature X is equal to 10 plus 190 times e to the minus kt. In part two, we're asked to find how long it takes for the body to reach 50 degrees C. Again, X is temperature and T is time in minutes. So let's make a start and see if we can answer both parts 1 and 2 of the question. Right. Now, for a body that is at a particular temperature, if it's cooling down, it's going to have a negative temperature gradient. If it's heating up, it's going to have a positive temperature gradient. Now, what do I mean by temperature gradient? Well, I mean that dx by dt is equal to something. First of all, this is the rate, dx by dt is the rate at which temperature changes with time t. And that is proportional in the Newton's law of cooling case to T. We're using X, aren't we? So is equal to X minus the surrounding air temperature, which we'll call theta S. This expression isn't much use to us until we can change it into some kind of an equation. What we really want is an equal sign here. So what we do is we write down dx by dt again, and we put that equal to something. Now, as I said before, if something is cooling down, it's got a negative temperature gradient. If something is heating up, it's got a positive temperature gradient. In this case, it's cooling down, so we're going to have a negative temperature gradient, and that is characterized by the negative sign there and a constant of proportionality, K. And let me just write that in a little more clearly for you. Multiplied by x minus theta s. Right, okay, so, if we've got a body like a block of metal, we'll assume that this metal is a cube. Then this has some temperature X, and the surrounding air temperature is theta sub s. We know what that's going to be in the question because we're already told that it's 10 degrees Celsius, but we won't bother putting that in for now. So what we've got here is an ordinary differential equation in the first case, which is dx by dt proportional to the temperature difference between the temperature of the body and the surrounding atmospheric temperature. We put an equal sign in here so that we get dx by dt is equal to minus k times, in brackets, x minus theta sub s, close brackets. Now, we can easily separate this ordinary differential equation. I'm going to call this equation 1, and I think I'll change the size of my pen. Right, okay. So we can now go ahead and separate out the variables. So if you've done any high school level mathematics, like A level in the United Kingdom, then you will know that this can very easily be separated out to give dx by x minus theta s equal to minus k, and we'll put the dt over here because I want to put integral signs in. Right? When you separate out an ordinary differential equation, you have to remember to put the integral signs in. Now, in this particular case, I'm going to substitute limits in where the integral signs are. So there's going to be a lower limit for the integral and an upper limit on both sides of this equation. So if we put limits in, such as x m for the maximum temperature and x at any time t, then we have to change the variable and use a dummy variable, which I will call phi. So we've got d phi over phi minus theta s, and that is equal to minus k. And again, we're specifying that the time starts at time 0 minutes and runs to time t minutes. So we have to change the variable dt to d tau, or rather we have to change the variable t to tau. Right, okay. Now we can go ahead and solve this equation. So again, using a bit of high school mathematics, this integrates on the left hand side to give the logarithm of phi minus theta sub s, and that is equal to, I'll make that look more like an equal sign. That is equal to k tau. And of course, we have to put the limits in. So we've got x m there for the maximum temperature, and x there, which is kind of our variable. And here, there isn't very much room to put the brackets in there, but we're going from 0 time to t. Okay, so now we can go ahead and substitute in the limits. So what we've got is the logarithm of x minus theta s minus the logarithm of xm minus theta s and that is equal to, well, it's just equal to k t. And I think you might have noticed that I've missed out a minus sign, which we'll just put here. So let me just erase that, and equals oops, pressing the wrong button there. Right, okay. You've got to watch me. I do make these mistakes. So there's a minus sign there. Now, the left-hand side can be rewritten as the log of x minus theta s, all divided by x m minus theta s. Put the modular signs in, equals minus kt. So what do we do now? Well, we don't want logarithms, so we take the exponential of both sides of this equation, which gives us, or leaves us with, x minus theta s over, let me make that line a little more distinct, over xm minus theta s, and that is equal to e to the minus kt. Right. So, moving on to the next page, what we now have is x minus theta sub s equal to xm minus theta s, and we'll put brackets around that, e to the minus kt. So you can see, hopefully see what I've done there. I've multiplied both sides of this equation here by xm minus theta s. So we multiply both sides by that, giving us this. Now then, that really is as far as we can go with that, although we could take the minus theta s to the other side of the equation. So okay, let's do that. So we've got x equals theta s. So we're adding theta s to both sides of this equation to give us the following. Okie doke. So that is as far as we can go without putting any values in that we've been given. But we do know, whoops, I can't even write now. We know that xm, the maximum temperature that the body has at time t equals 0, is 200 degrees C. That is a constant at that temperature of t, at that time of t equals 0. And we know also theta s, as I said earlier, was 10 degrees C. So x is equal to 10 plus 200 minus 10 e to the minus kt. I think I'm getting a bit more used to using this pen. My handwriting looks a bit neater, but you'll have to bear with me because I still have to improve. So anyway, what does this come out to be equal to? So the temperature at any time t, x is equal to 10 plus 190 e to the minus kt. Now, so that proves the first equation that we had here. X is equal to 10 plus 190 e to the minus kt. And if you remember, the question tells us that the body cools from 200 degrees C to 100 degrees C in 40 minutes. That means the half-life of that original temperature occurs in 40 minutes. So the half-life, which is 100 degrees C, occurs after 40 minutes. So let's go back to our equation and write down after 40 minutes x equals 100. So we have 100 equals 10 plus 190 e to the minus kt, because the whole point of this part of the exercise is to find the constant k to work out the final bit of the question. So if we rearrange this equation, we've got, maybe I should change to green. We've got 190 e to the minus kt. In fact, actually, that should be 40k. And because t is 40, we put the 40 in here as well. So we've got 40k. Go back to the green pen. And that's equal to 100 minus 10, which is 90. Okay. Right. So, dividing both sides by 190, we get let's just there we are. We get e to the minus 40 k equal to 9 over 19. Basically, what I've done there is let me just write this a little more neatly. I've just divided both sides by 10 to get 19e to the minus 40k equals 9 there, and that leads us to this. E to the minus 40k equals 9 over 19. And so we can now take logarithms. So we've got minus 40k because when you take logarithms of an exponential to any number, you just get that number. So like the log of e to minus 40k is just equal minus 40k. Okay, so that's equal to the log of 9 over 19. And you can simplify that and you get 1 over 40 log, well actually it's minus 1 over 40 log 9 over 19, but that is exactly the same as writing 40, oh sorry, what am I talking about? That's exactly the same as 1 over 40 log 19 over 9. And you can actually work that out as a number. And let me see what I've got here. So I think I've just left it as a logarithm. But if we work this out on a calculator, which I'll just do now, we've got 1 divided by 40 times the natural log of 19 divided by 9, and that comes out to be, or k comes out to be 0.01868 to 4 significant figures. Right, there you are. I've nearly gone off the page there. So now that we've found k, we can go back to this equation here, which actually I'll just mark in red as equation now. Let me see. Right, equation 2. Right, go back to the black, and I don't know why that little pop-up has come up, but it doesn't seem to want to disappear. So how do I, that's what we do. Right, okay, so that equation now becomes x equals, so x is equal to 10 plus 190 e to the minus 0.01868 times t. And the final part is, let me have a look. Right, so the final part in question in part 2 is to find how long it takes for the body to reach 50 degrees Celsius. So when x, so we want t, so we require t when x equals 50 degrees Celsius. So we substitute 50 in for x and equate that to 10 plus 190 e to the minus 0.01868 t. We don't know what t is yet, but it probably will involve taking logarithms again. If we simplify that expression, which actually I'll write down here again. So we've got 50 equals 10 plus 190 e to the minus 0.01868t. Right, so simplifying, you should be able to see what I'm going to do here. Right, we subtract 10 from both sides, leaving us with 40 on that side. So I've just swapped the sides around so that we've got 190e to the minus 0.01868t equals 40. And we can divide by 10 to get 19 on that side, multiplied by the exponential equals 4. So actually, another way of doing this is to say e to the minus 0.01868t is equal to 40 over 190, which is just 4 over 19. Right, okay. So what is t? Well, we've got an exponential here, and as I said before, if you take a logarithm of an exponential to any value a, you just get a. Okay? So I'll just delete that, and then it's not in the way of anything we're doing. So if you take the logarithm of the left-hand side, we've got minus 0.0. Let me just put that up a little bit. Oh, excuse me. Sorry about that. Right, here we are. Yeah, so I just write it a little bit closer to the top. E, we've got minus 0.01868t equal to the log of 4 over 19. Right? Now, what is a log of 4 over 19? Well, this is log of a fraction, so it's going to have a negative value. So let's work it out on the calculator, and we get the logarithm of 4 divided by 19 is equal to minus 1.558. Excuse me. So we've got minus 0.01868t equal to minus 1.55815, we'll call it. So I've actually gone to 1, 2, 3, 4, 6 significant figures there, but anyway, it doesn't really matter at this stage. The minus signs cancel, so that we have t equals 1.55815, all divided by 0.01868. And again, if we work that out on the calculator, which I'm going to do now, so 0.01868 comes out to be, or t comes out to be 83.41 minutes. And you can just leave the answer in that form. You can work out the point form 1 in seconds, and that would be 83 minutes and around 25 seconds. And that is the answer to the question. So just to recap, we've got a body that cools from 200 degrees C to 100 degrees C in 40 minutes. So we've shown part 1 is correct. X is equal to 10 plus 190 times the exponential to the power of k minus kt. And in part 2, we've found how long it takes for the body to reach 50 degrees C. And as you will remember, finding how long it takes the body to reach 50 degrees C depends on the value of the constant K, which has to be deduced, which we ascertained in this working here, particularly in green ink. So once we found the value of K, we could then resubstitute it back into that equation in part 1, and then substitute in the value of 50 for X and find T, just by normal algebraic expressions. So I hope that was okay for you, and that you will come back and also seek out some of my other videos. And until then, I bid you farewell. So thank you very much for listening, and see you soon. Bye.